In this lecture, we illustrate how to calculate the Fourier trigonometric series coefficients of a function that is given on a closed interval. The function that we will use for the example is sometimes referred to as the tent function. It is a tent function that is defined on the interval from 0 to 2. Let this tent function be the function f. On the interval from 0 to 1, we define f of t to be equal to t. On the interval from 1 to 2, we define f of t to be equal to 2 minus t. F of t is equal to 0 everywhere else. If the interval of definition of the function is centered at t equals 0, then the Fourier series of f, which we write as capital F as f of t, can be written as a sub 0 plus the sum from n equals 1 to infinity of the quantity a sub n times cosine n pi t over L plus b sub n times sine n pi t over L. A sub 0 is given by the formula 1 over 2L times the integral from minus L to L of f of t. For n greater than 0, these are the formulas for a sub n and b sub n. The constant L is the right endpoint of the interval of definition of f. Minus L is the left endpoint. Now observe that the interval of definition of our function is centered at t equals 1 and not at t equals 0. But the integral formulas for the Fourier coefficients require that the center of the interval of definition be at t equals 0. So we translate the functions so that the interval of definition of the translation is centered at t equals 0. Let this translation of f be equal to g of t. G of t should be equal to f of t plus 1. And so on the interval from minus 1 to 0, g of t is equal to 1 plus t. On the interval from 0 to 1, g of t equals 1 minus t. And everywhere else, g of t is 0. Let the Fourier series of g of t be equal to c sub 0 plus the sum from n equals 1 to infinity of c sub n times cosine n pi t over L plus d sub n times sine n pi t over L. Because the center of the interval of definition of the function g is now t equals 0, we can use these integral formulas to calculate the coefficients c sub 0, c sub n, and d sub n. We just have to replace f by g. C sub 0 is equal to 1 over 2L times the integral from minus L to L of g of t. L is equal to 1, and so the integral grows from minus 1 to 1. The integral of g of t from minus 1 to 1 is simply the area underneath the graph of g on the interval. The region under the graph of g is a triangular region whose area is half the base, which is 2, times the height, which is 1. And so the integral of g on the interval from minus 1 to 1 is 1, and c sub 0 is equal to 1/2. C sub n is equal to 1 over L times the integral from minus L to L of g of t cosine n pi t over L. L is still equal to 1. Because g of t is a piecewise function, we split up this integral into two pieces. The first integral grows from minus 1 to 0, and there g of t is equal to 1 plus t. The second integral grows from 0 to 1, and there g of t is equal to 1 minus t. Evaluating these integrals, we find that c sub n is equal to 2 minus 2 cosine n pi over n squared pi squared. If n is even, cosine n pi is equal to 1, and so c sub n is equal to 0 when n is even. On the other hand, when n pi is an odd multiple of pi, cosine n pi equals minus 1. And so c sub n is equal to 4 divided by the square of n times the square of pi when n is odd. The coefficient d sub n is equal to 1 over L times the integral from minus L to L of g of t times sine of n pi t over L. Now observe that g of t is an even function. And we know that sine n pi t over L is an odd function. Therefore, g of t times sine n pi t over L is an odd function. And the integral of an odd function on an interval centered at t equals 0, such as the interval from minus L to L, is 0. Therefore, the sine terms in the Fourier series of g are absent. C sub 0 is equal to 1/2. Because C sub n is non-zero only if n is odd, we let n be equal to 2k minus 1. So the rest of the Fourier series of g of t is the sum from k equals 1 to infinity of 4 divided by the quantity 2k minus 1 squared times pi squared, and then times cosine 2k minus 1 pi t. The dashed curve on the plot is the Fourier series of g up to k equals 2. The function g is the one-unit translation to the left of the function f. And so to obtain the Fourier series of f, we translate the Fourier series of g 1 unit to the right. Since g of t is equal to f of t plus 1, f of t is equal to g of t minus 1. And so the Fourier series of f of t should be the same as the Fourier series of g of t minus 1. We distribute the product 2k minus 1 pi to t minus 1 and find that the angle is 2k minus 1 pi t minus 2k minus 1 times pi. We use the trigonometric identity for the cosine of the difference between two angles. This cosine quantity should be equal to cosine of 2k minus 1 times pi times t times cosine of 2k minus 1 times pi plus sine of 2k minus 1 times pi times t times sine of 2k minus 1 times pi. Because k is an integer, sine of 2k minus 1 pi is 0. 2k minus 1 is odd, and so cosine 2k minus 1 pi is minus 1. And so the Fourier series of f is equal to half minus the summation k equals 1 to infinity of 4 divided by the square of 2k minus 1 times pi squared times cosine 2k minus 1 pi t. On the plot, we have the graphs of f and the Fourier series of f up to k equals 1. The 10th function in the example possesses special properties of continuity and differentiability that make the Fourier approximation tend to f pointwise as k tends to infinity. The Fourier series of f being made up of cosine functions is periodic. The period is the same as the length of the interval of definition of f, which is equal to 2 times L, or in this case, it's equal to 2. It is no surprise that we ended up with cosines for the trigonometric Fourier series of f. The translation g of f is an even function, and each cosine function in the Fourier series of g is an even function. Let us see what we get if instead of using the translation g to find the Fourier series of f, we use the even extension of f to find the Fourier series of f. Here we have the plot of f. Here we have the plot of the even extension of f. We designate the even extension of f of t as f sub even of t. For t between -2 and -1, f sub even of t is 2 plus t. For t between 1 and 2, f sub even of t is 2 minus t. And for the middle part, where t is between -1 and 1, we can use the absolute value of t. Because the domain of f sub even of t is centered at t equals 0, we can use these formulas to calculate the different coefficients for the Fourier series of f sub even of t. We will just have to replace f of t by f sub even of t. For b sub n, f sub even is even, being the even extension of f. Sine is an odd function. Hence, their product is an odd function. And therefore, the integral from minus L to L of f sub even times sine is 0. Therefore, f sub even has no sine terms in its Fourier series. L is now equal to 2. And because f sub even is an even function, we can just integrate from 0 to 2 and multiply the integral by 2. Therefore, a sub 0 is equal to half the integral of f sub even from 0 to 2. The integral from 0 to 2 of f sub even is just the area of one of the triangles. We know this area to be equal to 1. And so a sub 0 is equal to 1/2. We utilize the evenness of f sub even and the cosine functions for a sub n. The product of f sub even with each cosine function is an even function. Therefore, integrating only from 0 to 2, a sub n should be the integral from 0 to 1 of t times cosine n pi t over 2, plus the integral from 1 to 2 of 2 minus t times cosine n pi t over 2. We have two integrals for the formulation of a sub n because f sub even is a piecewise function. Carrying out the integration, a sub n is equal to the fraction minus 4 plus 8 cosine n pi over 2 minus 4 cosine n pi, all over the product of the squares of n and pi. If n is odd, cosine n pi over 2 is 0. N pi will be an odd multiple of pi, and so cosine n pi is minus 1. And so a sub n is 0 if n is odd. A sub n is also equal to 0 if n happens to be a multiple of 4, because then both n pi over 2 and n pi will be even multiples of pi, and so cosine n pi over 2 and cosine n pi are both equal to 1. The only case left for n modulo 4 is the case where n equals 4k minus 2 or 4k plus 2. Without loss of generality, we consider n equals 4k minus 2. If n equals 4k minus 2, then n pi is still an even multiple of pi, and cosine n pi equals 1. N pi over 2 will be equal to 2k minus 1 times pi, which is an odd multiple of pi, and so cosine n pi over 2 equals minus 1. And so, when n equals 4k minus 2, a sub n equals minus 16 divided by n squared times pi squared. We replace n by 4k minus 2, and so the Fourier series of f sub even of t equals half, plus the sum from k equals 1 to infinity, of minus 16 divided by the product of the squares of 4k minus 2 and pi times cosine of 4k minus 2 times pi t over 2. This is exactly the same as the Fourier series that we had obtained when we used the translation g to find the Fourier series of f. We carry this investigation further by taking a look at the situation where we extend f as an odd function across the y-axis. For the values of t that are between -2 and -1, f sub odd of t is equal to -2 minus t. Between -1 and 1, f sub odd of t is equal to t. We still have 2 minus t if t is between 1 and 2. This time, a sub 0 and the rest of the a sub n's are all equal to 0. This is because f sub odd, being an odd function, multiplied to 1 or cosine produces an odd function. And the integral of an odd function from minus L to L is 0. The product of f sub odd and sine n pi t over L, both being odd functions, is an even function. Consequently, we can integrate from 0 to L, L being equal to 2, and multiply the result by 2. With f sub odd being piecewise, there will be a couple of integral terms for b sub n. The first integral goes from 0 to 1, where f sub odd is equal to t. The integrand should be t times sine n pi t over 2. The second integral goes from 1 to 2, where f sub odd of t is equal to 2 minus t. The value of this integral is equal to 8 times sine n pi over 2 minus 4 times sine n pi all over n squared pi squared. If n is even, both angles in the sine functions are integer multiples of pi, and so both sine functions are 0. Therefore, b sub n is 0 if n is even. If n is odd, n pi is still a multiple of pi, and so sine n pi is 0. If n is odd, then n pi over 2 will be an odd multiple of pi over 2. And sine n pi over 2 will alternate between the values 1 and -1, starting with the value 1 if k starts at 1. So we can write the numerator as 8 times -1 raised to the k plus 1 power if we start k at 1. And we have the Fourier series for the odd extension of f.